2018 Advanced Higher Physics Examination. Question 3. Wheels on road vehicles can vibrate if the wheel is not balanced, and garages can check that each wheel is balanced using a wheel balancing machine as shown in figure 3a. Now you can see the wheel balancing machine there. You can see the wheel and you have the axis of rotation, so the wheel is going to rotate around that axis. Now the wheel is rotated about its axis by the wheel balancing machine, and the angular velocity of the wheel increases uniformly from rest with an angular acceleration of 6.7 radians per second. Now for 2 marks in part A, it says the wheel reaches its maximum angular velocity after 3.9 seconds. Show that its maximum angular velocity is 26 radians per second. Well, it's the same as linear motion equations. We have to put down first of all our initial angular velocity, which is going to be equal to 0. We put down our final angular velocity, which we have to find, but we're told it's 26 radians per second. We know the angular acceleration alpha, and that's going to be equal to 6.7 radians per second every second. And we also know that the time is going to be equal to, in this case, 3.9 seconds. So there's our basic data, W0, W, alpha and T, and just like the linear kinematics equations, we can put down the following. We can say omega, the final angular velocity, is equal to the initial angular velocity plus the angular acceleration times the time. That's how simple it is. So let's put in the numbers. Omega, our final angular velocity, will be equal to the initial one, which is going to be 0, plus, bracket in this one, alpha is the angular acceleration, which we are told is 6.7. I'm going to multiply that by time, which is going to be 3.9 seconds. So when we do our calculation, we can see that the answer is going to come to 26.13 radians per second. And we can put that into 2 significant figures. We say the angular velocity, the final angular velocity, is going to be 26 radians per second in 2 significant figures. So that's proven what we're asked for. We're asked to show that the maximum angular velocity at this particular time will be 26 radians per second, and that's what we've done. Question 3 continued, part B. After 3.9 seconds, the rotational kinetic energy of the wheel is 430 joules. And we have to calculate the momentum of inertia of the wheel, and that is for 3 marks. Well, go to your advanced higher relationship sheet and you'll find out that the equation for the rotational kinetic energy, EK, is going to equal to 1/2 times I, which is the moment of inertia, times the angular velocity squared. Now we know at 3.9 seconds, the angular velocity is going to be equal to 26 radians per second. So 26 radians per second. I'm already told that the kinetic energy is going to be equal to 430 joules. And we have to find out the moment of inertia I. That's our question we'll have to find out. So if you look at the equation, EK equals 1/2 I omega squared, we have to rearrange to find I. So a couple of algebraic moves, we multiply both sides by 2 to get double EK. 2EK equals I times omega squared. We want to find I on its own, the moment of inertia, so we have to divide both sides by omega squared. And we have 2 times the kinetic energy divided by omega squared, and that's going to give us the moment of inertia I. So all we have to do is put in the numbers, bracket 2 times the kinetic energy, 430. I'm going to divide that by the angular velocity at that particular time, 3.9 seconds, and we're told it's going to be 26 radians per second. And remember, you have to square that. And that's going to give us the moment of inertia of the wheel. So we do that in our calculators, we end up with the answer that the moment of inertia I is going to equal to 1.3, and the units will be kilogram metre squared. That's the moment of inertia. Part C. A brake is applied which brings the wheel uniformly to rest from its maximum velocity. The wheel completes 14 revolutions during the braking process. And for 4 marks we have to calculate the angular acceleration of the wheel during the braking process. Now let's draw attention to this idea of uniformly to rest. That just means that the angular acceleration will be constant, it will not change. Now, like all these problems, if we go back and think about how we did the linear kinetic problems, we had this setup. We had U, V, A, S and T. U being the initial velocity, V being the final velocity, A being the uniform acceleration, not changing, constant. S, capital S, would be the displacement, and T would be the time taken. So we can mirror those values into our rotational kinematics by replacing the U, V, A, S and T by our rotational equivalents. So omega naught would be the initial angular velocity. Omega would be the final angular velocity. Alpha would be the angular acceleration, which is uniform, which means it's constant. That's how these equations work. Theta would be the total displacement in terms of radians, angles, which is very important. And T would be the time. So that's the list that we would make, which is very similar to the linear kinematic one. So we'll take the linear kinematic one away now. That's not needed. And here we have our angular different values. So first of all, omega naught, well, we know omega naught has got to be 26 radians per second because that's the value which we were working with. So 26 radians per second. The final angular velocity is coming to a stop, a rest. That must be equal to 0. Our angular acceleration is what we are after. And our total angular displacement measured in radians will be the following. We have got 14 revolutions, but remember we can't just put down 14 revolutions, we have to put down it in terms of the radians that's passed through. And we know that in one revolution the angle gone through is 2 pi radians, so 14 revolutions will be 14 times 2 pi. That will be your angular displacement, if you can think of it that way. Time, we haven't got anything to do with time. So there's our 4 pieces of data that we know, and we can just go and look up the relationship sheet and we can find the equation which is going to show us what's happening. So we have to find alpha. So the one we choose is going to be omega squared is equal to omega naught squared plus 2 alpha theta. So that's very, very much the same as the linear kinematics one, v squared equals u squared plus 2as. We have a angular displacement, we have a final angular velocity, an initial angular velocity, and we have to find that alpha. So we've got everything in there except the alpha. So let's rearrange to find the expression in terms of alpha. We have omega squared, take away omega naught squared, I'll put that in a bracket, and that's got to be equal to 2 alpha times theta. We want to find alpha on its own, so we have to divide by 2 times theta, both sides, and we have this expression here, omega squared, final angular velocity, take away the initial angular velocity squared, and we're dividing that all by 2 times theta. Remember, theta is the amount of radians which the wheel has taken to come to a stop. So we put that number in, then that will give us a value for alpha. So therefore alpha is going to be equal to the angular acceleration, bracket, final angular velocity is going to be 0 squared, which is 0, take away 26 squared, and then divided by 2 times, and it's going to be this 14 times 2 pi. We can't forget that. Don't put in 14, that's just really the amount of revolutions we have. So once we have that into our calculator, we can do the necessary calculation. We end up with minus 3.8. Remember, it's angular acceleration, so it must be radians per second per second. and the minus sign confirms that the actual rotation is slowing down. It's going to have a negative acceleration. And that's how you go about doing part C. Final part of the question, part 2, calculate the braking torque applied by the wheel balancing machine. Well, if we go back to our linear equivalents of the kinematics, we know that the unbalanced force F is going to equal to the mass times the acceleration. So looking for a very similar expression, only to do with rotational mechanics. And we know from our data sheets that the torque T is equal to the moment of inertia times the angle of acceleration, angular acceleration. So torque equals I alpha is the rotational equivalent of force equals ma. Now we're asked to find that torque, and we know already the moment of inertia, was worked out in a previous question, was 1.3, and we know also that the angular acceleration worked out from the past questionnaire was minus 3.8. We'll just leave out units for convenience. So the torque is equal to, if you multiply it out, minus 3.8, and the units for torque are Newton meters. So the torque, which was necessary to bring this wheel to a stop, has a magnitude of 3.8 Newton meters. The minus sign means it's applied opposite to the forward motion of the wheel.